In the previous video, I mentioned that there are two different ways that we can multiply two vectors together. The first is called the dot product, and that was the focus of the previous video. The dot product, also known as the scalar product, multiplies two vectors together and gets a scalar as a result. The second way we can multiply two vectors together is called the cross product. The cross product multiplies two vectors together to get a third vector as a result, and because of this, it's sometimes called the vector product. The cross product is going to be the focus of this video. Now, the cross product is equally as useful as the dot product when working with vectors in computer graphics and programming. As we will see during this video, it enables us to find a vector that is mutually perpendicular to two other vectors. And that's just a fancy way of saying that this vector that we find is at a right angle or 90 degrees to both of the other vectors. Now, just as many areas of computer graphics and programming can benefit from the dot product, an equally large number of areas can benefit from finding a vector that is mutually perpendicular to two other vectors. And thus, a huge number of areas in computer graphics and programming can benefit from the cross product. Now, as I mentioned in the previous video, the cross product is thus named because of the symbol that we use when we're writing this operation. So if we had two vectors, if I had a vector A and a vector B, if I wish to multiply these two vectors together by using the cross product, we would write this as A cross B. Now, it is worth noting that just like with the dot product, some mathematical textbooks will write the cross product as a cross in a small circle, so you may see A cross B written like this. They both mean the same thing, they're just different ways of writing the cross product, they're just different notations, and it's all based on the preference of the author of that textbook. But if you see A cross B written with a cross like this, or A cross B written with a cross in a small circle, they both mean a vector cross product. Now, we've also mentioned earlier that the cross product is known by a different name. It's known as the vector product. And that's because the result of the cross product of two vectors is a third vector. So if I had A cross B, we know that's going to be equal to some vector, and I can call that vector an arbitrary name of V. But what is this vector V, and how do we calculate it? Well, being a vector, there are two pieces of information that we need to know about V. We need to know its direction, and we need to know its magnitude, or in other words, its length. So we need to find the direction of V, and we need to find the magnitude of V. Well, let's talk about the direction of V first. The direction of V is actually defined based on the relationship of vector A and vector B. So if we had vectors A and B, if I was to draw these on our whiteboard. Now I'm going to use lines just to keep this as neat as possible. And then jump back to my earlier layer. Fantastic. So if this was vector A and this was vector B, and they're floating around in 3D space, well, we can find a vector n hat, if you will. We're going to find a vector that we're going to call n hat, and because it's n hat, it's a unit vector, so it has a length of 1 unit, and this n hat vector has a very special property. It's going to meet both our vector A and our vector B at a right angle. That is to say that n is mutually perpendicular to A and B. So if I was to draw this on our diagram, n might look something like this. We have n hat, and we know that it's perpendicular to B and it's perpendicular to A. So it's mutually perpendicular to both A and B. For those of you who are familiar with polygons and surface normals, or perhaps you're familiar with mathematical planes and the normals of those planes, we can think of A and B as defining a perfectly flat surface. So if we have these two vectors, we can think of them as defining a flat surface. Whether that flat surface is a polygon or whether that flat surface is a mathematical plane, we can think of them as defining a flat surface. If A and B define that flat surface, the vector n is the normal vector to that flat surface. So if we had a polygon defined by two vectors, n is the normal to that polygon. For those of you who are familiar with modeling in 3D applications, n is going to be the normal to that polygon. Or if we had a plane, a mathematical plane, which is defined by two vectors that lie on that plane, then n is the normal vector to that plane. So whichever way you may be comfortable with, hopefully that helps give an idea of how n relates to a and b. Now if you're still having a hard time understanding how that relationship is set up, then imagine that we had a 3D scene, and in that 3D scene we had our 3D Cartesian axes. So we have our Cartesian axes with an x-axis, a y-axis and a z-axis. And let's imagine that our scene is oriented such that the xz plane is our floor of our scene, it's our ground plane, and that our y-axis is pointing directly up from the ground into the sky. Now if we created these two vectors a and b such that they lie on our ground plane, that is to say each vector can travel some distance in x and some distance in z, but they don't travel a distance in y, so they're running flat along the floor, then the cross product of these two vectors is always going to be parallel to the direction of our y-axis. It's always going to be parallel to that y-axis, because y is always parallel to x and z. Therefore any two vectors that run on the plane, the xz plane, their normal vector, if you will, their cross product is going to be perpendicular to the xz plane, and thus it's going to be parallel to the y-axis. Now this piece of information about how the result of the cross product relates to the two vectors that we're finding the cross product of is really important, because being able to find a vector that's mutually perpendicular to two other vectors is incredibly useful to us in computer graphics and programming. And later in this video we're actually going to explore just a handful of example problems where being able to find this mutually perpendicular vector is going to be very useful to us for solving those particular problems. Now hopefully the more observant of you out there are going to realize that there's actually two different unit vectors that will be mutually perpendicular to our pair of vectors a and b. One that points up, if you will, that we've drawn here as m, and the other that points down in the opposite direction. So which of these vectors is the correct vector? Because there's two vectors that can be defined as being mutually perpendicular to a and b. Which of these is the correct one? Well, the direction of the cross product vector is actually defined using what's known as the right-hand rule. Now we've seen the right-hand rule when we spoke about the 3D Cartesian coordinate system in volume 1 of this series. So using the right-hand rule, we hold our right hand out in front of us, and to start off with, for those of you who haven't encountered it, start with your fist clenched, so all of your fingers clenched into a fist, and just hold your arm, your right arm, out in front of you. Now extend your first finger, your index finger, so it's pointing out directly in front of you, as if you were pointing at someone in the distance who was directly in front of you. From there, keeping your finger extended out in front of you, extend your thumb so that it's pointing straight up, almost as if you were giving that person in the distance the thumbs up sign. So you've got your thumb sticking up and your finger sticking out directly in front of you. If you now extend your middle finger or your second finger so it's pointing out directly to the left of you, it should now be at a right angle to both your first finger and your thumb. So we're defining a set of axes, if you will. Now keeping your fingers in that relationship, now feel free to move your hand around and rotate your hand about your wrist. And what we're going to do, the way the right hand rule applies to our cross product, is that we assign our vector A to our thumb and our vector B to our first finger, and the direction that our middle finger is pointing in is going to be the direction of our n vector. So from our earlier drawing, if I was to match my thumb to A, match the direction of my first finger to B, we can see that my middle finger here is pointing up. So this vector that we first drew, this vector n, is the correct direction, and the vector that we drew second is the incorrect direction. So if we have A cross B, where A is the leftmost vector and B is the rightmost vector in that cross product operation, so A cross B, reading that from left to right, then we assign A to our thumb, B to our index finger, and the direction of the normal is defined by our middle finger. Now this actually brings up an interesting point about whether our cross product is commutative or not. So if we switched A and B around, in our cross product operation, so if we had B cross A, then what we need to do is we now need to assign B to our thumb and A to our first finger. If we do this and then match that to our diagram, we can see that our middle finger is actually pointing in the opposite direction. So the cross product is not commutative. That is to say that B cross A does not equal A cross B. Now it is worth noting that the length of the vector in both cases, and we will discuss how we find the length of that vector shortly, the length of the vector is the same in both cases, but the direction of the vector will point in the opposite direction if we switch around the two vectors in our cross product operation. So A cross B is not commutative. We cannot switch A and B around and get the same vector as a result. The vector will point in the opposite direction, and that is defined by our right hand rule. Okay, now before we move on and actually talk about the length of our vector v, some of you may have noticed that there is a scenario where the direction of our mutually perpendicular vector n isn't actually defined, and that's when A and B are parallel. So whether A and B are pointing in the same direction, or whether they're pointing in the opposite direction, if they're parallel, there's no single vector n that is defined, because if this was equal to A and this was equal to B, then any vector that's perpendicular to A is also going to be perpendicular to B, because they are the same direction. Thus there's an infinitely large choice of directions for our vector n. We could have a vector that points up here, it's going to be perpendicular to both. We could have a vector that sticks out here, it's perpendicular to both. We could have an infinitely large selection of vectors that sort of form a circle of vectors, if you will, for our n vectors. So there's an infinitely large choice of vectors. In that case, where A is parallel to B, and again that could be A and B are in the same direction, or A and B are in opposite directions, in those cases the n vector actually collapses down to the vector 0, 0, 0. So when A and B are parallel to each other, the cross product and the n vector, it collapses down to a vector that has no length and it has no direction. The cross product becomes this 0 vector that has the components 0, 0, 0. Now that's really important and worth keeping in mind, because if we're finding the cross product of two vectors in a computer program, you need to be aware of what happens when those two vectors do become parallel to each other. Because if you're then taking this cross product and using it for something else later on, you're using it to solve some problem, or maybe in a 3D application you're using it to constrain some object's orientation, or one of the many other uses that we might use the cross product for, it could actually have a huge impact on the way that you're using this vector if our two input vectors become parallel, because suddenly this vector that you're relying on so heavily becomes nothing. It has no direction, it has no length, and that could make everything else that you're basing on that vector explode, for lack of a better word. Alright, so now that we've discussed in detail the direction of the cross product vector v, this vector that we get as a result of crossing A with B, let's now talk about the length of v. Well, the length of v is not necessarily a unit vector. If I was to return to my earlier diagram and clear a little space, so bear with me while I erase some of our workings, there we go. If I was to return to my earlier diagram, we could actually draw the result of the cross product of A cross B as something like this. So this is the vector A cross B, because it travels in the same direction as n, but it could have a different length. So we could actually rewrite our earlier equation here of A cross B is equal to V as actually being A cross B is equal to some scalar value s multiplied by our unit vector n, because we know that the result of A cross B is some scaled version of that vector that's mutually perpendicular to A and B, and we know that if we multiply that vector n by a scalar value, we're going to scale up that vector, so some scalar value is going to give us the vector that's the correct length for A cross B. But what is this scalar value that defines the length of A cross B? Well, the length of A cross B is actually defined as a relationship between the length of A the length of b, and the angle between those two vectors, so the angle theta between those two vectors. Now this relationship is actually pretty similar to our dot product relationship. If you recall our dot product, again as I clear some space just so we're near our diagram, our dot product from the previous video is a dot b is equal to the length of a times the length of b multiplied by the cosine of the angle between them. Well, the length of our cross product vector, so the length of a cross b, which we know is equal to our scalar s, so the length of a cross b, which is equal to our scalar s, is actually equal to the length of a multiplied by the length of b multiplied by the sine of the angle between them. So these two are very similar. The dot product deals with the length of a, length of b, and the cosine of the angle. The length of our cross product is the length of a, the length of b, and the sine of our angle. So knowing this, we could actually rewrite, I will erase the dot product so we don't confuse anyone, because we're not dealing with the dot product here, we are dealing with the cross product. There we go. We could actually rewrite our cross product equation as a cross b is equal to the length of a multiplied by the length of b multiplied by the sine of the angle between those two vectors multiplied by our unit vector n that is mutually perpendicular to both vector a and vector b. So this is our first definition of the cross product. We're saying a cross b is equal to the length of a multiplied by the length of b multiplied by the sine of the angle in between them multiplied by the unit vector n that is mutually perpendicular to both a and b. So we can see that the result of a cross b is a vector, because we've got a scalar value multiplied by a vector that gives us a vector. That vector is going to have the same direction as n, and its length is going to be dictated by this scalar value, because we're taking a vector that has a length of 1 and we're scaling it up based on the scalar value, the length of a, length of b, and sine of the angle between those two vectors. Now, just like the dot product has two definitions, one that's an equation that involves the magnitude of the vectors and the cosine of the angle between them, the other being an equation that involves the components of the vectors, so too does the cross product. So we can define the cross product in terms of the components of a and b. Now this is very useful, because if we know vector A and we know vector B in terms of their components, then we can find the cross product of A cross B by using their components, and that will tell us this vector that is mutually perpendicular to both A and B. And since we know that vector is very useful to us, it's going to be useful to be able to find it knowing only the components of vectors A and B. Now we could also, just like we did with the dot product, we could also, once we found A cross B, rearrange this equation and use it to find some other piece of information. For example, we could use it to find the sine of the angle between A cross B, though that's very rarely the use for a cross product, because if we were trying to find the sine of the angle between A and B, it would be easier just to use the dot product to find the angle between A and B and then calculate the sine of that angle. But it is worth pointing out that if you wanted, you could, once you've calculated this vector value, rearrange this equation in any way that you wanted to work out any of the other pieces of information in this equation, though again, that's very rarely the way that we'd use the cross product. So just as we did with our dot product, we could say that A and B are equal to certain values in their components, and then we can start using those and putting them into our equation to work out what the component version of the cross product is going to be. So I'm going to bring up a new whiteboard. I'm going to hide out everything we've done up until this point. Fantastic. So I'm going to say that A is equal to the vector x1, y1, z1, and B is the vector x2, y2, and Z2. So just like when we assigned the components of A and B in the dot product video. And we know that if these are the components of our vectors, then we can write them as a combination of our I, J, and K Cartesian vectors, where A is equal to x1i plus y1j plus z1k, and B is equal to x2i plus y2j plus z2k. So we can write A and B in terms of combinations of those three Cartesian vectors I, J, and K. Therefore, the cross product of A crossed with B becomes the cross product of x1i plus y1j plus z1k crossed with x2i plus y2j plus z2k. We can see that if this is equal to A and this is equal to B, then A cross B is going to be the same as this crossed with this. So this is a very similar approach that we took when we were finding the component version of the dot product. The only difference is we're now finding the cross product of these two vectors, not the dot product of those two vectors. So just like we did in our dot product video, we're actually going to expand this. So if we were to expand this, the first thing we get is this term multiplied, or rather crossed with this term crossed with this term, and this term crossed with this term. So we're going to get x1i crossed with x2i plus y2j plus z2k. Then we're going to add to that y1j crossed with x2i plus y2j plus z2k. And we're going to add to that z1k, so z1k crossed with x2i plus y2j plus z2k. We can then continue, so this is equal to this, and we can then continue on and expand this further. And to expand this further, we're going to take this term and cross it with this term, plus this term and cross it with this term, plus this term and cross it with this term, plus this term cross this term, then cross that term, and then that term, and so on for the rest of our equation. Now we saw how we could do this in the previous video with our dot product, where we had this term dot, this term, then this term dot, this term, and so on. And we saw how that eventually that became two scalar values multiplied together, multiplied by two vectors dotted together. There was a sort of step in between, but eventually it became this sort of way that we could write it as, for example, our first part would become x1, x2, in this case, because it's a cross product, I cross I. Now there was the stage in between, but to save some time, hopefully, because it's the exact same thing as we saw with our dot product, the only difference is we're using a cross product here. Hopefully everyone's going to be happy with me skipping that middle step and simply writing our x1i crossed with x2i as x1, x2 multiplied by I crossed with I. And we can do the same now for all of the other terms of our equation. So we're going to add to that x1i crossed with y2j. That's going to give us x1, y2, I crossed with j. Then we can add to that x1i crossed with z2k. So that's going to give me x1, z2, I crossed with k. Then we can add to that y1j crossed with x2i. That's going to give me y1, x2, j crossed with I. I can add to that y1j crossed with y2j. That's going to give me y1, y2, j crossed with j. Then I'm going to add to that y1j crossed with z2k. That's going to give me y1, z2, j crossed with k. Fantastic. And then moving on, we're going to add to that z1k crossed with x2i. So that's going to give me z1 x2k crossed with I plus z1k crossed with y2j. That's z1 y2k crossed with j plus z1k crossed with z2k. z1 z2k crossed with k. So the equation we've got so far is this equation right here. Now again, just with our dot product, this may look like a horrible equation. It may look extremely complicated, so much going on, it could look quite intimidating and quite a horrible equation. But if we break it down, we're going to see that it's actually quite simple. We have a series of scalar multiplications, just like with our dot product, and these are very easy to calculate. We're just multiplying components of the two vectors. And in this case, we have a series of cross product operations between pairings of our Cartesian vectors. Now, if we use our definition of the cross product from earlier, where we said A cross B is equal to the length of A multiplied by the length of B multiplied by the sine of the angle between them multiplied by that mutually perpendicular unit vector, then we can actually calculate each of these cross products between our Cartesian vectors. And the first thing we can see is that we know our Cartesian vectors are unit vectors. So if we were to put our Cartesian vectors into this cross product definition, no matter which vectors we're crossing with each other, they are all unit vectors. That means the length of A is always 1 and the length of B is always 1. So for this above equation, we can actually simplify down our A cross B such that it's actually just equal to, and I will erase all of this and rewrite it, it simplifies down to being equal to the sine of theta multiplied by the unit vector that is perpendicular to both A and B, because we know if we had the length of A, which is 1, multiplied by the length of B, which is 1, that gives us 1, multiplied by the sine of theta times n, well, 1 times anything is the same as that thing, so we can cancel out the length of A and the length of B and remove those from our equations. Now we also know the relationships between our three Cartesian vectors. We know we have these three vectors and they follow our x, y and z axes, which means this would be our I vector, this is our j vector, this is our k vector, and we know they are all perpendicular to each other. They're all at 90 degrees to each other. Now again, just as when we had our dot product and we had all of the dot product operations here, we have the cross product operations of a number of these Cartesian vectors, and there are actually two different types of combinations of these vectors. Either we're crossing a vector with itself, or we're crossing a vector with one of the other Cartesian vectors. If we're crossing a vector with itself, then we know that the angle between any vector and itself is 0 degrees. So our cross product operation for a vector crossed with itself becomes the sine of 0 degrees multiplied by that vector n. And we know that the sine of 0 degrees is 0. Thus this becomes 0 multiplied by that vector n, which becomes a 0 vector. It's a vector where all of the components are 0. We have 0 in x, 0 in y, and 0 in z. And this agrees with our earlier definition where we were saying if a and b are parallel to each other, which if we're crossing I with I they are, then we know that we get this 0 vector as a result. Well, the reason is because the sine of a 0 degrees angle between these two vectors, so the sine of 0 is 0, and 0 multiplied by anything is going to give us this 0 vector. Also, if we look at our equation here where we're using this 0 vector, if we take a 0 vector and we multiply it by a scalar value, any scalar value multiplied by 0 is going to give us 0. Any scalar value multiplied by 0 is going to give us 0, and 0 for the z component. So a 0 vector, a vector with 0 in all three components, in this case because it's a 3D vector, multiplied by any scalar value is still going to be this 0 vector. And if we think about this 0 vector, that means all of this would become a 0 vector. If we add that 0 vector to any other vector, it has no impact on the vector result. If we took a vector, let's say a vector 1, 2, 3. So this is just an example. If we had a vector 1, 2, 3, and we add a 0 vector to it, it has absolutely no impact on the result. The result is 1 plus 0, which is 1, 2 plus 0, which is 2, 3 plus 0, which is 3. It has no impact whatsoever on the result of that operation, which means that all of those 0 vectors in our above equation can be completely taken out of the equation. They have no impact. So we know that we get a 0 vector when we're taking the cross product of any of our Cartesian vectors with itself. So when those vectors are parallel, which means it's a Cartesian vector crossed with itself, then we can remove that from our equation. So that's going to be this term, where we have I crossed with I. So all of this becomes a 0 vector which has no impact on our result. So we can remove that from our equation. Then we have I crossed with j. Well, that's not crossed with itself, so that's fine. I crossed with k, that's fine. J with I, that's fine. J crossed with j, they're going to result in that 0 vector. So we can remove all of this because it has no impact on our result. Fantastic. J crossed with k, that's fine. K with I is fine. K with j is fine. And here we have k with k, they're parallel. The sine of the angle between them is 0, and therefore this is going to become a 0 vector that has absolutely no impact on the result of our equation. So already, just by analysing the first case of how our Cartesian vectors can combine together, we have simplified down our equation significantly. Okay, so the other type of combinations that we have between our Cartesian vectors is when we're crossing a vector with one of the other Cartesian vectors. And we know in that case, we're going to be crossing it with a vector that's perpendicular to that vector. It doesn't matter which combination we have. All of the combinations where we cross one of our Cartesian vectors with one of the others, they're always at a right angle to each other. So that means A cross B becomes the sine of 90 degrees multiplied by our unit vector n, and we know that 90 degrees, well, the sine of 90 degrees is a value of 1, so therefore all of these become 1 times that unit vector n, and therefore they are just simply equal to the unit vector n. And we know that unit vector n is the vector that's mutually perpendicular to the two vectors that we're crossing, and it's defined by the right hand rule. So we can go through and we can look at these two vectors that we're crossing in each case, and we can use our right hand rule to find a vector that will be the result, this vector n, the result of these two vectors being crossed together. Now this is easiest to show rather than try and explain in words without actually doing it. So if I'm taking I and I'm crossing it with j, I'm going to assign I to my right thumb, j to my right first finger, and if I align my thumb and finger to I and j in that diagram, you can see my middle finger, the result, our result that's going to be this vector n, is pointing out in the direction of k. So we can say that I crossed with j, knowing that we're going to get a unit vector, and that unit vector is mutually perpendicular to I and j, and we know that k is a unit vector, and it's mutually perpendicular to I and j, and looking at our right hand rule, we can see that when we cross I with j, we get a vector pointing in this direction, rather than a vector pointing in this direction. We can see that the result of I crossed with j is this vector k. Now again, this all comes down to the fact that I and j are unit vectors, so we remove the length of A and the length of B from our equation, that gets removed. Then we know that I and j are 90 degrees to each other, so the sine of 90 becomes 1, so that gets removed. It means all we're interested in is the unit vector that's the result. The unit vector can be found with the right-hand rule, and we know, of course, that it is going to be mutually perpendicular to both of these. So we assign our thumb to I, our first finger to j, and we find that it's a vector that's going to be pointing in this direction, not this direction. And it's the vector that's mutually perpendicular to I and j, which happens to be the vector k. So I crossed with j simply becomes the vector k. We can now repeat this for all of our other combinations. So I crossed with k. I'm going to assign my thumb to I, my first finger to k. When I do this and align it with the diagram, you'll notice my middle finger is pointing down in the opposite direction. So I crossed with crossed with k rather is equal to negative j, because if I assign my thumb to I, my first finger to k, we're going to get a vector that's pointing down in this direction. Now we know j is mutually perpendicular to I and k, but it's pointing in the wrong direction. So if we take minus j, we'll get the vector that points down in the opposite direction, and that's going to give us the vector that's equal to I crossed with k. We can then move on, j crossed with I, so I'm going to assign my thumb to j, my first finger to I. When I align that with my diagram, though that is kind of complicated, there we go, I can see that my middle finger is sticking out in this direction, so that is equal to negative k. So j crossed with I is equal to negative k. J crossed with k, I assign my thumb to j, my first finger to k. When I do that, I can see my middle finger is in the direction of I. So j crossed with k becomes I. Fantastic. K crossed with I here. So thumb assigned to k, first finger assigned to I. When I do that, I can see that indeed my middle finger is sticking in the direction of j. So k crossed with I becomes j. Fantastic. And k crossed with j, so thumb assigned to k, first finger assigned to j. When I do that, my middle finger is pointing in the opposite direction to I, so k crossed with j is equal to negative I. Now before I continue, I want to clear some space below our equation, so I'm going to erase everything that we've drawn down here because we no longer require it. So I'm going to just clear some space so that I can continue working with the equation directly below where we'd got to. So just bear with me a second as I erase some space. And I do want to double check that I have space. Yes, fantastic. So we can see we've got our equation, and what I first want to deal with is these terms where we have a negative vector. Now I know if I have a vector k, if I was to make that into a negative k, I know that what I've done is I've inverted the direction of the vector. I've got a vector now that travels in the opposite direction. So likewise, if I was to take, for example, negative j, if I was to write negative j as positive j, I know my vector now is travelling in the opposite direction than it was originally. At the same time, if I have a scalar value and I'm multiplying a scalar value by a vector, so if I have s times v, if I was to invert that scalar value, negate that scalar value, I know that that's going to have the same effect as flipping our vector. It's going to make the vector travel in the opposite direction. So s times v, whatever direction that travels in, minus s times v is going to travel in the opposite direction. We know this when we looked at the scalar multiplication of a vector. We saw the effect that a negative scale factor has on that vector. So we know if I was to negate my scale factor, my scalar value, my vector is going to travel also in the opposite direction. Therefore, if I was to negate both the vector and the scalar value, each of these on their own would flip the direction of my vector. So if I had a vector and I negate the vector, it's flipped to the opposite direction, but then if I then negate the scalar as well, it's going to flip to the opposite direction of this vector, which is back to how it was originally. So if I was to negate the vector and the scalar value, that's going to have no impact on the resultant vector. And what that allows me to do, it allows me to remove the negative here from in front of vector j and instead place it in front of the scalar value. So if we were adding x1 z2 multiplied by minus j, that's the same as subtracting x1 z2 times j. So I just kind of wanted to prove that so that I don't skip any of the sort of important proof that shows that this is mathematically sound. So I'm doing the same here where we had minus k. I've removed that from in front of k and placed it in front of the scalar. And we also have minus I here. So I'm going to remove the minus sign from in front of I and place that in front of our scalar value. So now what I'd like to do is I'd like to collect together the terms of I, j, and k. So I'm going to rewrite this. And the first thing I'm looking for is terms of I. So we have this term of I. So y1 z2 multiplied by I. And then we're subtracting. I'm going to cross through this so we know we've dealt with it, which I guess I should do before I circle someone else. Fantastic. We're then subtracting this term of I. So minus z1 y2 times I. I'm now interested in terms of j. Well, we have this guy. So we could add z1 x2 times j. So we've dealt with him. We also have this term up here. So we're subtracting x1 z2 times j. I'm also interested in terms of k. Well, we have this term of k right here. So x1 y2 k. And this term of k, the final term in our equation. So minus y1 x2 times k, which hopefully you can see I could now factorize this, if you will. I could put these into parentheses, so we have y1 z2 minus z1 y2 multiplied by I, because if we had some scaled value of I and we had some other scaled value of I and then we subtracted one from the other, we'd get the difference in between them. Well, that's the same as saying we have this scale that we're going to use just as a scalar value, subtract the other scalar value from it, and then simply scale our I vector up to that length. So we're able to factorize that into parentheses. So that's our first terms dealing with I. I'm then going to add to that z1 x2 minus x1 z2 minus, or rather multiplied by j. So z1 x2 minus x1 z2 multiplied by j. And then I'm going to add to that x1 y2 minus y1 x2 multiplied by k. Well, if we've got some term multiplied by I, plus some scalar value multiplied by j, plus some scalar value multiplied by k, we know that we could equally just write this as the vector, where this scalar value is our x component, so y1 z2 minus z1 y2. This scalar value is our y component, so z1 x2 minus x1 z2. And this scalar value right here is our z component, so x1 y2 minus y1 x2. This right here is the component definition of the cross product. Now this might seem quite difficult to remember. You may think you're going to have a hard time remembering how we calculate the cross product in terms of the components of the vector. But there's actually a nice sort of visual trick that you can use that makes remembering how to compute the components of the vector for our cross product very easy. So to do this, I'm going to need to bring up a new whiteboard because I've run out of space on my existing one. And the first thing I need to write down is, if we recall, our vector A is equal to x1, y1, z1, and our vector B is equal to x2, y2, z2. And what we're trying to find is a crossed with b. So we could equally write this as the vector x1, y1, z1 crossed with x2, y2, z2. So the first thing, if you're trying to find a cross product to do, if you're wanting to use this little visual trick, is to write the vectors that we're crossing in terms of column vectors and write one vector crossed with the other vector left to right here as column vectors. Now the next stage of this trick is to write another copy of both of these vectors directly beneath our existing set. So I'm going to take this vector here with its 3 components and I'm going to write another copy directly beneath it. So here we have a column of numbers, and that column should have 6 numbers. We should have x1, y1, z1, and then a repeat, x1, y1, z1. And we're going to do the same here for this vector. So we're going to take a copy of this vector and write it directly beneath it. So x2, y2, z2. Again, a column of 6 numbers where we have our vector and then a repeat of the components of that vector. Now we know the result of our cross product is a vector, and that vector has 3 components in its result. So for the first component of the result, we're going to take the first row of our columns of numbers, which have 6 numbers in each column. So the first component of the result, we take the first row of these columns of numbers and we cross it out. We write a line through it. We're not interested in those numbers. What we're interested in is the next 2 rows beneath those numbers. So again, for the first component of our result, we take the first row of our columns of numbers and we cross through it. We're not interested in that. What we're interested in is the next 2 rows of numbers beneath that. So we're looking at these 2 rows of numbers here. But how do we use those to get our first component of the result? Well, there's a very small rule that we need to remember. And that rule is we take the top left number multiplied by the bottom right number, and then we subtract the bottom left number multiplied by the top right number. And it's easy to remember this starting top left if we draw a cross. Since we are doing the cross product, if we draw a cross, then that's going to be easy to remember. So we take the top left multiplied by the bottom right and subtract from that the bottom left multiplied by the top right. So that's going to give us y1 multiplied by z2. So y1 multiplied by z2, and we subtract from that bottom left multiplied by top right. So z1 multiplied by y2. This is the first component of our result. If we then repeat this, so we now have the second component of our result, what we need to do for the second component, we take the second row of our numbers and we put a cross through it. We're not interested in it. We cross those numbers out. What we're interested in is the next 2 rows of numbers beneath them. And we apply our small rule to these numbers. We take the top left multiplied by the bottom right. So z1 multiplied by x2, and we subtract from that the bottom left multiplied by the top right. x1 multiplied by z2. So again, we are looking for our second component of the result. So we take our second row of numbers and we put a cross through it. We're interested in this next 2 rows of numbers directly beneath them, and we apply our simple cross, if you will, where we take the top left and multiply that by the bottom right, and we subtract from that the bottom left multiplied by the top right. So we can now repeat this for our third component. So for our third component, we're looking at the third row of our numbers and we put a cross through it. We're not interested in those numbers. What we're interested in is the next 2 rows of numbers beneath that. And in these rows, we apply our rule. Top left multiplied by bottom right, subtract bottom left multiplied by top right. So top left, x1, multiplied by bottom right, x2, and we subtract from that bottom left, y1, multiplied by top right, x2. So if you compare this, y1 z2 minus z1 y2, z1 x2 minus x1 z2, x1 y2 minus y1 x2, I know it's going to be hard to remember that, but if you were to compare this, let me draw on the layer, thank you. It's the exact same thing that we had here. So by using that nice visual helper, if you will, you can very quickly, if you have two vectors and you're trying to find the cross product of them, if you can't remember the result of the cross product in terms of the components, you can use this visual trick where for the element, the component of the vector you're trying to find, you cross through the row of that vector, you look at the next two rows directly beneath it, and you apply the rule top left multiplied by bottom right, and subtract from that bottom left multiplied by top right. And that will give you the result of the cross product in terms of their components. So hopefully, I think you'll agree that that's a lot easier to remember than simply the components and the equations of the components that we have written in the component form of the cross product. I personally much prefer this sort of more visual hands-on method for calculating it. Alright, so now that we've actually seen what the cross product is and how we can calculate it, let's actually use our component definition of the cross product to find the cross product of two vectors. So I'm going to scroll down, and if I had a vector A, which is equal to the vector 1, 2, 0, and I had a vector B, which is equal to the vector minus 5, 3, 0, I'd like to find the cross product of A cross B. Now to do this, I'm going to use our visual helper, if you will, but if you wanted to, you could also use just the component definition where we know which of the components we're multiplying together and what we're subtracting from that, and you could simply take each of these components and put them into that equation, which of course, if you were implementing this on a computer in a computer program, that's exactly the approach you'd take. You'd simply write an equation that takes the corresponding components of each of the vectors, multiplies them together, subtracts them from other quantities, and the likes. But since I'm working here on the whiteboard, I want to use our visual helper to help me to calculate this manually, the result of the vector product of A and B. So to do that, I'm going to write my vector A. So I have 1, 2, 0, crossed with B, minus 5, 3, 0. And we know the first thing I need to do is write another copy of these directly beneath my first set. So I've written another copy of each vector directly beneath the first set. I know my result is going to have 3 components, and for the first component I take the first row of numbers and I put a cross through it because I'm interested in the next 2 rows of numbers directly beneath that. And for that, I'm going to take top left multiplied by bottom right. So that's going to give me 2 multiplied by 0, and subtract bottom left rather, multiplied by top right. So that's top left multiplied by bottom right, subtract bottom left multiplied by top right. So that's 2 multiplied by 0 minus 0 multiplied by 3. So that's the first component of my result. For the second component of my result, I'm going to take the second row of numbers and put a cross through it. I'm then interested in the next 2 rows of numbers that are beneath that row, and I'm going to apply my rule. Top left multiplied by bottom right, so that's 0 multiplied by negative 5, minus bottom left multiplied by top right, so minus 1 multiplied by 0. And then for my third and final component, I take the third row of numbers here in our columns of numbers, and I put a cross through it because I'm interested in these next 2 rows of numbers, and I'm going to apply our rule. Top left multiplied by bottom right, so 1 multiplied by 3, minus bottom left multiplied by top right, 2 multiplied by negative 5. Now that we have that, we can actually work out these values. So this is equal to, well, 2 multiplied by 0 is 0, minus 0 multiplied by 3 is 0, so 0 minus 0. 0 multiplied by a negative 5 is 0, minus 1 multiplied by 0 is 0. 1 multiplied by 3 is 3, minus 2 multiplied by 5 is negative 10. So that is equal to 0 minus 0 is 0. 0 minus 0 is 0. 3 minus minus 10 is 3 plus 10, which is 13. So the result of A cross B is the vector 0, 0, 13. Now notice when I chose the values for our two vectors A and B, which I'm going to rewrite down here. So A was 1, 2, 0. A was 1, 2, 0. And B was minus 5, 3, 0. Minus 5, 3, 0. When I chose the values, the components of these vectors, I specifically chose them so they don't travel in Z. So what I was doing, I was saying we have our Cartesian axes, we have X, Y, and Z. I was specifically saying that these vectors lie on the XY plane. They do not travel in Z. So because of that, we've got two vectors that lie somewhere on our XY plane. That means the cross product of these, if it's mutually perpendicular to these, we know it's either going to be in the direction of the Z-axis or the direction of the negative Z-axis, and we can see that it is. It is in the direction of the Z-axis. The cross product of those two vectors travels in the direction of the Z-axis and has a length of 13 units. So you notice it doesn't travel in X and Y, it only travels in Z. That's exactly what I was expecting because I chose these vectors so that they don't travel in Z, which means they lie on the XY plane. Thus, a vector that's mutually perpendicular to two vectors on that plane is going to either be in the direction of positive Z or negative Z. Fantastic. So before I move on to look at another example, there's actually one final piece of theory that I'd like us to look at in this video, and that relates back to our original definition of the cross product. So I'm going to bring up a new whiteboard, and if you recall, when we first defined the cross product, we said that A cross B is equal to the length of A multiplied by the length of B multiplied by the sine of the angle between them multiplied by that mutually perpendicular unit vector n. And we had a diagram that looked something like this. We had our vector A, our vector B, we had the angle between them, then we had that mutually perpendicular vector n, and then we said that A cross B was some scaled version of that vector. Well, if we were looking at these vectors here and we were looking directly down in the opposite direction to our n vector, we could imagine looking at these vectors as if our whiteboard here was the plane that these two vectors lay on, and our normal vector is sticking straight out the screen towards us. So we'd see something that looks a bit like this. We'd see a vector A, a vector B, and some angle between them. Now, we could think of our vectors as defining a triangle. If I was to put a dotted line down here, we could think of our vectors as defining a triangle. If we had our two vectors touching at a point, and then they travel in the two different directions, if we took the endpoints of each of those vectors and used those 3 points, we could define a triangle. Now, in volume 2 of this series, we saw how we could apply trigonometry to calculate the area of an arbitrary triangle, just like this triangle right here. So if you recall, we saw that the area of an arbitrary triangle is equal to the half of the length of one of the edges, multiplied by the length of one of the other edges, multiplied by the sine of the angle between them. And that was written as the area is equal to half AB sine of theta. Now, if we're applying that to this triangle, we can see that A here, the length of one of the edges, is really the length of our vector A, because A is a vector, so we can't just have A in that equation. What we really need is the length of the edge, which is the length of vector A, and the B in our equation really is the length of this edge here, which is the length of vector B. So the area of a triangle, as defined by our vectors, would be equal to half the length of vector A multiplied by the length of vector B, multiplied by the sine of the angle between them. Now, if we took this idea, this concept, and extended it to construct a parallelogram as defined by these two vectors, we'd have another copy of A that sits up here, and we'd have another copy of B that connects here. And we know that if we know the area of this half of the parallelogram, the area of this half is the same. So the area of the whole parallelogram is 2 times the area of this triangle. So the area of our whole parallelogram is 2 times a half times the length of A times the length of B times the sine of the angle between them. So allow me to clear that part of our working. So the area is equal to 2 times a half times the length of A times the length of B times the sine of the angle between them. Well, 2 times a half is just 1, and 1 times anything is just anything. So the 2 and the half cancel each other out. And that means the area of the parallelogram that is defined by our vectors A, B, and the angle between them is equal to the length of A times the length of B times the sine of the angle between them. But let's have a look back up here at our cross product. Notice how similar these are. We have the length of A multiplied by the length of B multiplied by the sine of the angle between them, but in the case of our cross product, we're then multiplying it by that unit vector. But we know if this unit vector, because it has a length of 1, that this is the scale factor of that unit vector, and thus this is the length of the vector that results as our cross product. So if I was to find the length of our cross product, that length is equal to the length of A multiplied by the length of B multiplied by the sine of the angle between them, because we are multiplying that by a unit vector and that has a length of 1. So the length of the resultant vector is that scale value. So notice, length of A, length of B, sine of theta, length of A, length of B, sine of theta. What we're saying is that the length of the cross product between A and B is equal to the area of the parallelogram as defined by A and B. So this could be quite useful, because if we know A and B, we know their components, well then we can use the component definition of the cross product to find the vector A cross B. We can then find the magnitude of that vector using the theories that we've seen in previous videos, and with that, that magnitude of that vector is equal to the area of the parallelogram defined by A and B, and if we wanted, we could then halve that value to find the area of the triangle defined by A and B. And this could be quite useful. If we had a triangle in 3D space, then we could construct some vectors to represent that triangle, take the cross product of those vectors, then take the magnitude of that cross product, then halve it, and that would give us the area of our triangle in 3D space. So that might actually be quite useful to us. Alright, so now that we've got all of that theory out of the way, let's look at another example of using the cross product, but this time I'd like to give it a little bit of context. So let's say, as I scroll down real quick, let's say that I've got a triangle in 3D space. I've got some triangle floating in 3D space, and that triangle is defined by the 3 points of that triangle. The first point is V1, and that has the coordinates 0, 2, 2. The second point is V2, which has the coordinates 0, 1, 4. And the third point is V3, which has the coordinates 1, 1, 2. Now this triangle floating out there in 3D space, what I'd like to do is I'd like to find the normal vector of this triangle. We know the normal vector is going to be a vector that is perpendicular to the plane defined by that triangle. So I'm interested in finding that normal vector to our triangle. Now to do this, we can actually construct some vectors using the 3 points of our triangle. If I constructed a vector that travels from point 3 to point 1, I get a vector that travels up along this edge, like so. If I then constructed a vector that travels from point 3 to point 2, I get a vector that travels along this edge, like so. Now I could call this vector A, and this vector b. If I take the cross product of a and b, I know that's going to give me a vector that is mutually perpendicular to both, which I know is going to be a vector that is perpendicular to that triangle. That's going to be our normal vector. So we can construct some vectors using the points of our triangle. If we then take the cross product of those vectors, it's going to give us the normal vector of our triangle. So that's incredibly useful in computer graphics, and it's something that is done quite often, even if you don't realize, internally for 3D applications and graphics APIs that are finding the normal vector for various polygonal objects, or other polygonal faces. So we've got our 3 points, and I want to define a vector A and a vector B. So we know that vector A is traveling from point 3 to point 1. So if I was to represent these points as position vectors, so position vector V1 is equal to 0, 2, 2. Position vector V2 is equal to 0, 1, 4. And position vector V3 is equal to 1, 1, 2. Then I could find this vector by using our simple position vector mathematics that we'd already seen in an earlier video. So I want to start at V3, I'm going to travel down negative V3 to the origin, and then I'm going to travel from the origin back up to V1 with a positive V1. So A is equal to a positive V1 minus V3. Again, we've seen that in our earlier video covering position vectors. So that means it's equal to V1 is 0, 2, 2, minus V3 is 1, 1, 2, which means it's equal to 0 minus 1 is minus 1, 2 minus 1 is 1, and 2 minus 2 is 0. Fantastic. B is going to travel from V3 to V2, so it's equal to V2 minus V3, which is equal to V2 is 0, 1, 4, minus V3 is 1, 1, 2, which is equal to 0 minus 1 is minus 1, 1 minus 1 is 0, and 4 minus 2 is 2. So our vector A is equal to minus 1, 1, 0, and our vector B is equal to minus 1, 0, 2. And what I'm interested in doing is finding the cross product of these two vectors to find that normal vector of our triangle. So I'm going to take A cross with B, which we know is equal to, I'm going to write these in column form now, minus 1, 1, 0, crossed with minus 1, 0, 2. And I'm going to use our visual trick, if you will, to find the cross product of these two vectors. So to do that, I'm going to write another copy of the vectors directly beneath the existing copy. So I've taken these and I've copied them directly beneath, and the same for our right vector, our B vector. And then for the first component of my result, I take the first row of numbers and I put a cross through it. I'm then interested in the next two rows of numbers, and we take top left multiplied by bottom right minus bottom left multiplied by top right. So that's going to be 1 multiplied by 2, top left multiplied by bottom right, and I'm going to subtract from that bottom left times top right. So 0 multiplied by 0. For the second component of our result, I'm going to take the second row of numbers and put a cross through it. I'm then interested in the next two rows of numbers beneath that, and we follow our rule. Top left multiplied by bottom right, so 0 multiplied by minus 1, minus bottom left times top right, minus 1 multiplied by 2. So top left multiplied by bottom right, minus bottom left multiplied by top right. Fantastic. And then for our third component of the result, I take the third row of numbers and I put a cross through it. I'm then interested in the next two rows of numbers directly beneath that. And again, we apply our rule. Top left multiplied by bottom right, so minus 1 multiplied by 0, minus bottom left multiplied by top right. 1 multiplied by minus 1. So if we work that out, 1 multiplied by 2 is 2, minus 0 multiplied by 0 is 0, 0 multiplied by minus 1 is 0, minus 1 multiplied by 2 is minus 2, minus 1 multiplied by 0 is 0, minus 1 multiplied by minus 1 is minus 1. So 2 minus 0 is 2. 0 minus minus 2 is 0 plus 2, which is 2. And 0 minus minus 1 is 0 plus 1, which is 1. So A cross B is equal to the vector 2, 2, 1. So this vector 2, 2, 1 is the normal vector for our triangle. Now if we wanted, for efficiency reasons or for any other reason, if we wanted a normal vector, then we could then normalize this vector using the techniques that we've seen in earlier videos. But this vector isn't normalized, so it's not a unit vector, but it is a normal vector for this polygon. It is a vector that's perpendicular to the plane defined by that polygon, but if you wanted a normal vector, a unit normal vector, you would need to now normalize that vector. Now for those of you who've worked in 3D applications creating polygons from scratch, or perhaps you've worked with 3D graphics APIs such as OpenGL, and you've either heard people or maybe documentation mention that when you're defining triangles, for example, in those programs, the order in which you specify the points is going to have a direct impact on the direction of the surface normal. Well, this is why it has an impact on the direction of the surface normal, because the order that we define our points in is going to affect how the internal mechanics of whatever that application or API is using to define these two vectors. It's going to affect their internal mechanics, and as a result, the vectors will get defined differently, and as a result of that, we know if we have the cross product of vectors, how those vectors relate to each other with our right-hand rule is going to define the direction of that normal. So if you put the order of the points in differently, the vectors internally will be defined differently. Therefore, there's a chance that our cross product will be pointing in the opposite direction. So if you've ever wondered why they say the order of the points as you input them is going to have an effect, it's going to control the direction of the surface normal, of the normal vector, it's exactly because of what we've just looked at here. It's because of the way these vectors are defined, and thus the way the cross product is calculated on those vectors, giving us a normal vector that points in one of two directions. Alright, so now that we've actually covered all of the theory that I wanted to cover in this video, along with some examples, it is now time for you to work through just a few questions on your own. So in order to do that, I'm going to bring up a nice clean whiteboard. Okay, so question 1. In this question, we're going to have a vector A that is equal to 4, 7, and minus 1, and a vector B that is equal to 2, minus 3, and 5. And what I'd like you to do is find the value of A cross B. So go ahead and pause the video and attempt to find the value of A cross B. Once you have a solution, or if you get stuck, unpause the video and I will work through the answer here on the whiteboard. Alright, welcome back everyone. So we're trying to find A cross B, which we know is equal to the vector 4, 7, minus 1, crossed with 2, minus 3, 5, which we can apply our visual trick, if you will, to help us find the cross product of these two vectors. So I'm going to write another copy of each vector directly beneath it. So 4, 7, minus 1, and 2, minus 3, 5. And then we know the first component of our result. We look at the first row of numbers and we put a cross through it, and we're only interested in the next two rows of numbers that are directly beneath that row, and we apply our rule, top left multiplied by bottom right minus bottom left multiplied by top right. So top left multiplied by bottom right is 7 multiplied by 5 minus bottom left multiplied by top right. So minus 1 multiplied by minus 3. For the second component of our result, we look at the second row of numbers and we put a cross through it because we're interested in the next two rows of numbers that are directly beneath that, and we apply our rule. Top left multiplied by bottom right, so minus 1 multiplied by 2 minus bottom left multiplied by top right, so minus 4 multiplied by 5. And then for the third component of our result, we take the third row of numbers and we put a cross through it because we're interested in the next two rows of numbers directly beneath that, and we apply our rule. Top left multiplied by bottom right, so 4 multiplied by minus 3 minus bottom left multiplied by top right, so minus 7 multiplied by 2. Now that we have that, allow me to erase this. Fantastic. And we can continue evaluating this. So this is equal to, well, 7 multiplied by 5 is 35. Minus 1 multiplied by minus 3 is positive 3, so minus 3. Negative 1 multiplied by 2 is minus 2. Minus 4 multiplied by 5 is 20. 4 multiplied by negative 3 is minus 12. Minus 7 multiplied by 2 is 14. So 35 minus 3 is 32. Minus 2 minus 20 is minus 22. And minus 12 minus 14 is minus 26. So the result you were looking for, the vector that is the cross product of A cross B, is the vector 32 minus 22 and minus 26. So if you got that correct, congratulations. If you didn't, the first thing to make sure is that you either calculated the value correctly using that visual trick and that you used that trick correctly, or if you use the component definition as is, you correctly inserted all of the numbers into that definition. If you did that, then just be careful with the evaluation, because it is very easy to make simple numerical mistakes when you are multiplying these numbers together and adding and subtracting them. So just make sure that you double check all your results, because you should be getting the vector 32, negative 22, negative 26. Fantastic. So I'm going to move on to question 2, and just to be safe, I'm going to use a new layer just in case we need lots of working. So question 2. Now in this question, I'm going to tell you that a triangle, a triangular polygon, is defined by the following 3 points. It's defined by a point 1, 5, 3. It's defined by a point minus 2, 0, 1. And it's defined by the point 9, 4, 7. So a triangle is defined by those 3 points. And what I'd like you to do is to find the unit vector normal for that polygon. Now don't worry about whether the normal is pointing in one direction or the other direction. So it may be pointing in one direction, it may be pointing in the opposite direction. Either is fine, as long as you approach this problem with the correct method. You may get one or the other depending on how you approach it, but either result is fine. What I'm looking for here is more that you have the correct approach to the problem rather than having a specific vector as an end result. So again, these 3 points define a polygon, they define a triangle, and I'd like you to tell me the unit vector normal for that polygon, please. Alright, welcome back everyone. So this is similar to the problem that we saw earlier. We need to construct some vectors out of our points. Now again, I'm not worried how you chose to construct your vectors. So you may have chosen different points for the vectors to start at and end at, but your overall workflow should be the same. So you should be constructing vectors out of the points as the first step in your workflow. So personally, I'm going to construct a vector from our third point to our first point, and another vector from our third point to our second point. So that means my first vector A is equal to this point minus our third point, because it goes from our third to our first, so it's this one minus this one. Again, we saw that in our position vector video, so 1, 5, 3 minus 9, 4, 7, which is equal to 1 minus 9 is minus 8, 5 minus 4 is 1, and 3 minus 7 is minus 4. Fantastic. Now vector B is going from our third point to our second point. That probably would have been better had I written these as column vectors, so let's do that for B. It might be just a little easier to see what's going on. So B is going from our third point to our second point, which means we are taking our second point and subtracting our third point from it. So minus 2, 0, 1, minus 2, 0, 1, minus our third point, which is 9, 4, 7, 9, 4, 7, and that is equal to minus 2 minus 9 is minus 11, 0 minus 4 is minus 4, and 1 minus 7 is minus 6. So we have our two vectors. We have our vector B and our vector A there. And now what we need to do is we need to calculate the cross product of these two vectors, because that's going to give us a vector that is normal to that polygon. So we're calculating the cross product of A and B. So that's the cross product of minus 8, 1, and minus 4, crossed with minus 11, minus 4, and minus 6. So I'm going to use our Visual A to calculate this cross product. So I'm going to write another copy of our numbers. And minus 11, minus 4, minus 6. Fantastic. And then we know our result. The first component of our result, we take our first row of numbers, put a cross through it, take the next two rows of numbers and apply our rule. Top left multiplied by bottom right. Subtract bottom left multiplied by top right. So minus 4, minus 4. And the few slip-ups here and there I've had in this video with actually saying this out loud shows to you how used to using the visual version of this, where I simply just go, draw across, oh okay, it's 1 multiplied by minus 6 minus 4 multiplied by minus 4. I'm so used to that visual version rather than saying top left multiplied by bottom right minus bottom left multiplied by top right. I just don't remember it like that. I simply go cross, okay, these guys minus these guys. I'm so used to that visual version. So the few slip-ups I have, I do apologize for those, but it's simply because I'm used to drawing this visually rather than saying it out loud. So that's our first component. Our second component, we take the second row of numbers here, put a cross through it. We're interested in the next two rows of numbers, and we follow that rule. Top left multiplied by bottom right, so minus 4 multiplied by minus 11, minus bottom left multiplied by top right, so minus 8 multiplied by minus 6. And then for our third component of the result, we put a cross through our third row, next two rows of numbers. Minus 8 multiplied by minus 4, minus 1 multiplied by minus 11. Fantastic. So I'm going to erase these to clear some space. Fantastic. And let's start evaluating this. So 1 multiplied by minus 6 is minus 6. Minus 4 multiplied by minus 4 is positive 16, so we're subtracting 16. Minus 4 multiplied by minus 11 is positive 44. Minus 8 multiplied by minus 6 is positive 48, so we're subtracting positive 48. Minus 8 multiplied by minus 4 is positive 32. 1 multiplied by minus 11 is minus 11, So we're subtracting minus 11, which means we're adding 11. Which means we have a vector for the result of our cross product as minus 6 minus 16 is minus 22. 44 minus 48 is minus 4. And 32 plus 11 is 43. So the vector that's the result of our cross product is this vector, minus 22, minus 4, 43. Now again, based on how you define the vectors involved in that cross product, you may have ended up with a vector that was equal to the vector in the opposite direction, so 22, 4, minus 43. You should have ended up with one of these two vectors, or you may have ended up with a vector with a different length, of course, if you were using different vectors to define this. So you may have ended up with one of these two vectors, you may have ended up with a different vector, but we're not actually done yet, because when I set the question up here, I asked for the unit normal vector. This is not a unit vector, this is quite a long vector, and I'm asking for the unit normal vector, which means we need to normalize this result. So if I was to call my normal vector n, we know that n normalized, so if I was to call my normal vector n, I know that n is a unit vector, so the normalized version of n is equal to n over the length of n. So if this is n, we want to divide it by its length to get that unit vector version of our normal vector. So that means I need to work out the length of n. The length of n, I'm not going to be able to quite fit it on. The length of n we know is equal to the square root of x squared plus y squared plus z squared. X is minus 22, so minus 22 squared plus y is minus 4 squared plus z is 43, so 43 squared. I'm not even going to hazard to attempt to work this out in my head, so I am going to bring up a calculator. So minus 22 squared, that's the same as 22 squared, so 22 squared is 484, so this is equal to the square root of 484 plus minus 4 squared is 16 plus 43 squared is 1,849. So 1,849, which is equal to the square root of, again using a calculator, 484 plus 16 plus 1849 is equal to the square root of 2,349. So the square root of 2,349. Which means the length of our vector is approximately equal to, using our calculator, 2,349, and I want to find the square root of that. It's approximately equal to 48.466 units. So 48.466 units. What that means is to find our unit vector normal, I need to take our vector, divide it by 48.466 units. That means I need to take each component of our vector here and divide it by 48.466 units. Now I don't really have enough space on my whiteboard, so I'm going to bring up a new whiteboard. And we know that n is equal to the vector, and that vector was minus 22 in x, it's minus 4 in y, and it's 43 in z. And we know that the length of m was equal to 48.466 units. So what I want to do is I want to find our unit vector n. It's equal to n divided by the length of m, which is equal to n divided by 48.466. I'm going to take each of these components and divide it by 48.466. So our unit vector n is equal to, it's going to be minus 22 divided by 48.466 in x. I will write this as a row vector just so I can refer to these results without scrolling. Then minus 4 divided by 48.466 in y, and 43 divided by 48.466 in Z, which, using a calculator, tells us that n hat is equal to minus 22 divided by 48.466 is minus 0.454. So I guess this is approximately, since we approximated this value, this is also approximately. And that was for our first value, which I have now forgotten. Fantastic. So minus 22 divided by 48.466 minus 0.454 in x minus 0.454 in x. In y, it's minus 4 divided by 48.466, which is minus 0.082, which we can round to 0.83, so 0.083, and that is a negative. Minus 0.083 in y, and in z it's equal to 43 divided by 48.466, which is 0.887. So 0.887. And we can check that this is close to being a unit vector very quickly. I know the square of negative 0.454 is the same as the square of 0.454, so I'm going to say 0.454 squared plus 0.083 squared plus 0.887 squared. That's equal to 0.999, so very close to 1, which means the square root is very close to 1. Therefore, the length of n is approximately 1. So this is the normal vector, the unit normal vector for our triangle. Now, of course, if you constructed your vectors in a different way, you may have got a normal that points in the opposite direction. So if this is the case, your normal will be equal to minus 1 multiplied by n hat, which of course will be the vector positive 0.454, positive 0.083, and negative 0.887. So if you had a vector that was close to this one or close to this one, of course, depending on how you rounded your numbers, you may have slightly different results due to the rounding error involved. But if you had numbers that were close to this one, then you got the correct result. Now again, what I was more concerned with was your approach to the problem. So we construct vectors using our points, we then find the cross product of those vectors to get a normal vector, but of course I was after a unit normal vector, which meant we needed to normalize that vector to get a normal vector that has a length of 1. So that is the answer for question 2. Alright, so question 3, this is going to be the final question of this video. I will bring up a new whiteboard for it. Question 3, now this is going to be a little bit of a tricky question, certainly an interesting question. So in this question, I'm going to say that we have a ball, and this ball is rolling in a straight line from the point, so this point is the point 105, so 105, and it's rolling to the point 409. So we have a ball, and it's rolling in a straight line from the point 105 to the point 409. And now what you'll notice is we're not moving in y, which means we are rolling on the xz plane. So what I'd like you to do, knowing that this ball is rolling in a straight line from this point to this point, I'd like you to find a vector that represents the axis of rotation for that ball. So again, we know the ball is rolling from this point to this point in a straight line. I'd like you to find a vector that represents the axis of rotation for that ball. Okay, welcome back everyone. So this question does require a little bit of thinking, but it's actually not too bad at all. So if we have our ball and it's rolling in a straight line along the ground, then we know if we're rotating and rolling in a straight line along the ground, our axis of rotation is always going to stick out to the side of the ball. If that's how we're rotating, then our axis of rotation sticks out to the side of the ball. In other words, our axis of rotation is perpendicular to the direction of travel. But how can we calculate this axis? Well, we know it's perpendicular to the direction of travel, but that doesn't actually narrow it down, because as we saw earlier, if one vector is perpendicular to another vector, there's actually an infinitely large range of vectors that are perpendicular to another vector. So that doesn't actually narrow it down for us. But what else do we know? Well, from logic, if we think about this, we know because the ball is rolling on the XZ plane, and we know from our experience of rolling a ball along the ground, that if it's rolling in that plane, this axis of rotation is going to be parallel to this plane, or in other words, it's going to be perpendicular to our y-axis. If this was our y-axis, we know it's going to be perpendicular to our y-axis, and we know it's perpendicular to our direction of travel. So if we could find a vector that represents our direction of travel and a vector that represents our y-axis, we could take the cross product of these vectors, and that will give us the axis of rotation for that ball. So we have a vector that represents our y-axis. If we remember, our Cartesian vector j represents our y-axis, and our Cartesian vector j has the components 0 in x, 1 in y, and 0 in z. And we can create a vector that represents our direction of travel by taking the endpoint 409 and subtracting from it the start point 105. So if I wanted a vector t that represents our direction of travel, that is equal to the endpoint 409. I'm going to write this in column format just so it'll be a little cleaner. So 409, and I'm going to subtract from that endpoint our start point 105, and that tells us our direction of travel is the vector 304. And we can see that if we start at 1 in x and travel 3 units in x, we do of course end up at 4 units in x. If we start at 5 in z and travel 4 units in z, we of course end up at 9 in z. So we have our vector j, it's equal to 0, 1, 0, and our vector t is equal to 3, 4, 0. And what I want to do is I want to find the cross product of these, so we get that vector that is mutually perpendicular to both of these vectors, and that is going to be our axis of rotation. Now, of course, depending on the order in which you cross these two vectors in, you may get a vector that points in a different direction, and depending on how you defined our y-axis, you may not have defined it as 0, 1, 0, you may have defined it as 0, 10, 0, or some other value. So depending on how you defined our y-axis, you may get a vector that has a different length. But just as with the previous question, what's important here is not the result itself, it's the method you've used in order to solve this problem. So the method we've used is to construct a vector that represents our direction of travel. We've realized that it's going to be perpendicular to this vector and to our y-axis, so we've constructed a vector that represents our y-axis, and now we're going to take the cross product of those vectors. So I'm going to take the cross product of j crossed with t, which is equal to 0, 1, 0 crossed with t, which is 3, 0, 4. 304, fantastic. And if we follow our visual aid here, I write another copy below our existing vectors, and then for the first component of our result, I take the first row of numbers and I put a cross through it. There we go. I'm interested in the next 2 rows of numbers beneath that. Top left multiplied by bottom right, 1 multiplied by 4, minus bottom left multiplied by top right, minus 0 multiplied by 0. Second component, second row of numbers, put a cross through it, next 2 rows of numbers down, top left multiplied by bottom right, 0 multiplied by 3, minus bottom left by top right, 0 multiplied by 4. Third component, third row of numbers, put a cross through it, next 2 rows of numbers, top left multiplied by bottom right, 0 multiplied by 0, minus bottom left multiplied by top right, 1 multiplied by 3. So if I erase these just to clear some space, fantastic. So we can now continue to equate this. So 1 multiplied by 4 is of course 4, minus 0 multiplied by 0 is 0. 0 multiplied by 3 is 0, minus 0 multiplied by 4 is 0. 0 multiplied by 0 is 0, minus 1 multiplied by 3 is 3, and that gives me the vector 4 minus 0 is 4, 0 minus 0 is 0, and 0 minus 3 is minus 3. So I've got a vector 4, 0, 3. That vector is a vector that's mutually perpendicular to both the direction of travel and the y-axis. So this is one of many vectors that could represent our axis of rotation. Again, your vector may have a different length. It could be a scaled version of this vector, which also means it could be traveling in the opposite direction based on how you constructed this problem. But as long as you followed your own workflow that was very similar to mine, where we constructed these two vectors and used those to find the cross product of those vectors, which gives us that axis of rotation just as defined by a vector, then that's absolutely fine, and that is the correct result. If you weren't able to solve this problem, that's okay. It was a little bit challenging, especially as I didn't give very many hints, if any hints, when I actually set the question. Hopefully, by watching through the solution here, you can see how I've applied the cross product and the theory we've seen in this video to find a vector, and of course a vector represents a direction which can be used as an axis of rotation. So I found a vector that represents the axis of rotation for a ball when we roll a ball in a straight line between these 2 points. So we have covered a lot of ground in this video. So just to recap really quickly, we have seen firstly that the cross product of two vectors, which is also known as the vector product, can be defined in two ways. We've seen that it can be defined A cross B is equal to the length of A multiplied by the length of B multiplied by the sine of the angle between them multiplied by that mutually perpendicular unit vector n. We've also seen that A cross B can be defined in terms of the components of the two vectors, and that is for the first component of the result, y1 z2 minus z1 y2. For the second component of the result, it's z1 x2 minus x1 z2, and for the third component of the result, it's x1 y2 minus y1 x2. So we've seen that our cross product can be defined in two different ways. The way that's most useful to us, of course, is the component definition, but it's also useful to know how it relates to that mutually perpendicular vector, because that's our biggest use for the cross product, is to find a vector that is mutually perpendicular to A and B. We've also seen how that vector, the direction of that vector, is defined by using our right hand rule, where A is represented by our thumb, B is represented by our first finger, and the resultant vector n, and of course the resultant vector A cross B, is represented by our middle finger. We've seen how the magnitude of the resultant vector is equal to the parallelogram defined by A and B. So if we had A and B, the area of that parallelogram is equal to the length of our cross product vector. So we've seen how the magnitude of that vector is equal to the area of the parallelogram defined by A and B. And we've also seen a selection of problems that can be solved using the cross product, which hopefully illustrates just how powerful not only the cross product itself is, but vectors in general are for solving problems in computer graphics and programming. And we've really only just scratched the surface of all the possible things that we can do with the cross product. And when you take the cross product and you start combining it with the dot product to solve problems, there's a huge amount of things that you can do, a huge amount of otherwise very complicated problems that become incredibly simple when we use the cross product or when we use the dot product to help us solve those problems. So that is going to conclude this video. I really hope you've enjoyed this video over the cross product, and thank you a lot for watching.